Welcome to my talk. This is my first talk for a larger audience, so I'm quite nervous. Um, okay, I want to talk to you about the lessons I learned for the development of reusable firmware in the last months. Okay, at first, like it was already mentioned, I work for Leica Geosystems. Leica Geosystem produces different devising for surveying solutions. On this image, you see some of our devices. Each of these devices can communicate with each other. They share some kind of common functionality, and each of the devices contains at least one microcontroller unit. Most of the devices smaller than one. So each of these devices needs to be maintained for at least 10 years. And all few years, we release a new generation of these devices. This creates some problems. The problems are mostly based on changes and complexity. We are starting with complexity. These are some devices which Leica produced over their way over 100 years history. The first device is from the 40s, I think, and then go on until the last device, which is quite recent. Like you see from the images, each of the devices gets more features. It gets way more functionalities. It combines different kinds of levels or different kinds of departments. So in the new devices, we have machine learning in it. We have motorization and so on. So the problem now is this cannot be handled by single developers. This needs to have some kind of collaboration between software teams. Also on the firmware development, which means classical firmware development, one team creates the whole firmware, everything is fine. Now, if multiple teams needs to interact on the same firmware, you need to have some kind of collaboration. If you have collaboration, every part deploys its software, and somebody needs to integrate it, which means the person which integrates it needs to have the power to still configure the system, which means he is responsible for the resources, he is responsible for priorities of threads and so on. And this is an issue because most software doesn't allow it easily, at least in the current state. Maybe to the software, to mention, nearly all our software is written in C++, and also the MCU software uses some kind of operating system. Currently, mostly Sapphire, some use FreeRTOS, some use quite old operating systems which are not supported anymore. Okay, so complexity is one issue. The other issue is changes. So, like I mentioned, we have a maintenance time for over 10 years, which means each product needs to live 10 and some years. This is a problem because at first, over the time, hardware can change. Also in a product which is already released. We've seen it in the last years with the chip shortage. Quite soon, you need to adapt something where you were thinking you will never touch this code again. This is an issue. And like I mentioned, we have already different kind of operating systems. If you want to reuse our software, this is also an issue. So this is one thing where I would disagree with the speaker from the morning. You should not rely on one operating system because each operating system is disliked by at least one person in the company, which means everybody wants to have a different operating system and everybody wants to develop their software somehow different. So the last kind of changes which could affect you are requirement changes. For everybody which worked on a product, this is more or less daily business. Mostly they are not so terrible. Sometimes they are quite annoying, but this is not a huge issue. So, like I mentioned, we had lifecycle issues in the last year. This was one solution to fix the lifecycle issue. This image is, the first code fragment is from the code which was already released, and the second one is the adaptation for a new MCU. And like you see from the pictures, this is a little bit like Finding Waldo. They look quite similar, but if you don't see it, in the second one, the number is different. So this was done to adapt to a new pin layout. And this was done by copying the whole code base, then adapt nearly 24 places where the pin layout was used. And then we had two different products. This approach is called mutation in software development. Mutation means you copy a code base You adapt them somehow that they is not exactly the same like before, and now you have two code bases. Which means with each mutation, it is quite harder to merge them together. And this is not so nice, because now if you get the requirement changes, for example, you need to fix both code bases. And we are speaking about 24 lines of changes, but the copy of over 20,000 lines of code. Which means now you have more maintenance effort than you previously was thinking about. So we tried something to fix this. This is where we came up with later on to merge the code bases. This is quite simple approach, only as a hotfix. And what we have done is we created more or less a constant for the configuration of the pin layout, which is provided in a different kind of header file. And the header file is injected in the other code bases where it fetches this value from. Now we have still a mutation, but only on one header file. And most of the code bases can share it again. This means we have a new level of abstraction, and this somehow reduces the problem. Doesn't fix it, it reduces it. So, and similar approaches you can choose for each kind of changes. Which means, when we want to do it over a larger scale, we need abstraction layers. And everybody loves abstraction layers, so everybody has created at least one, and the task is not nice, but it needs to be done. So the most important thing is the hardware abstraction layer. If you cannot adapt your hardware from your software product, each change in hardware will end up in huge changes of your software. The second one is the middleware abstraction. Middleware abstraction means, at first, the abstraction of your operating system. The abstraction of all third-party library you cannot control. And the reason for that is quite simple. If an API change happens on the baseline, your legacy code will probably not adapt, but your code need to adapt. If you don't have an abstraction here, and you need to maintain a life cycle some years in the future, you are screwed, because you don't know what was the API change, why was it changed, and has some impact on our product. To avoid this, you need a middleware abstraction. And business logic is still one part. This is, for us, the most important part, but you need to structure it somehow. You need to be able that you can combine your business logic in a proper manner. So now let's discuss about this abstraction layers. No, we discussed for the benefits and drawbacks. At first, the benefits from reusable firmware is we can reuse functionality. I mean, that's in the name. And also we can manage system complexity. If you write a code which has some kind of domain knowledge, you don't need to get this knowledge again because you don't need to write it again. The other point is, more or less the main point, it reduces dramatically development time if you can reuse your software. Everything you don't need to write again for each generation will speed up your time to the market. And this is what nearly every company is more or less about. It is important that we fit our time to the market. If your product releases too late, you're screwed. It has drawbacks. If you want to write reusable firmware, you have way higher effort. One example would be the mutation. To make a mutation in code goes rather quick. But it is not reusable. So you need to invest upfront in abstraction layers and in different kind of measurements that you can benefit from it on the long term. The other one is if you make an abstraction layer, for example, a hardware abstraction layer, you need to consider all dependencies from all products which can happen somewhere. This is not an easy task, and probably you will fail by at the first try. And the last thing is, if you have abstraction layers and you create a regression on your abstraction layer, you fuck up all systems. So then you are totally screwed. Which means if you go this route that everybody shares some code, you need to have a proper testing base over all levels. There is no excuse. You need it, else you will fail. So what needs to be done if we want to create reusable firmware? At first, we need to create a hardware abstraction layer. We also need to create a middleware abstraction. We need to separate all our business logic in small parts that we can combine it like we want. All this fun doesn't bring anything if we are not able to separate our business logic. We need to separate it by requirements. Each requirement could be fulfilled without another requirement in the place. And also, we need to enable integration step, like I mentioned previously, that we can control our system in the end. Our systems are more or less real-time systems. We have not impossible deadlines, but it should be real-time. And like I mentioned, we need to consider testing for all over all stages we have. So, hardware abstraction layer. I assume most of you have already worked with some kind of hardware abstraction layer. And I assume you found it horrible. Hardware abstraction layer, only to get it done, is more or less a high-level API on over low-level hardware access. So, in hardware abstraction layer, there are a lot of hardware abstraction layer on the market. They have some issues. The first one is, like already mentioned yesterday, I think, sometimes the development quality is questionable. Other point is, each hardware abstraction layer is vendor or architecture specific, which means CMSIS only works on Cortex-M architectures, and if you go in the direction of SD or NXP, they have their own HAL, but this is vendor specific. The other point is there are some hardware abstraction layers. For example, Sapphire OS has an own hardware abstraction layer, which then would bind you to an operating system. This is also something you don't want, which means in the end, you need your own hardware abstraction layer. A lot of people worked on it, tried it at least in the past, but you will still, at first run, need your own. Or at least I don't know one which you can easily use. For an hardware abstraction layer, you should consider testing all over the place, which means if you make a hardware abstraction, your hardware abstraction needs to be mockable if you want to test it on the upper layer. Also, it makes sense to consider testing right from the beginning, testing and simulation, because you will need it later. It's quite easy to simulate it if you consider it. And if you can simulate it, you can test the rest of your logic independently. So, for this you have the normal possibilities you have for abstraction. You have runtime abstraction, interfaces, callbacks, or you have compile time abstractions like template, header injection, or link injection. The approach I prefer looks something like that. It's more or less a mixture between header injection and template injection. You see, I have a template. I call it base GPIO, which has one template parameter. The template parameter is a tag type. For people which are not familiar with tag types, this is more or less an empty struct, which has a fancy name. This tag type is then used in the line 3 and line 4 to gather some information over the system. The first one is, what I need to know is, I have a tag type which can be called STM32. And based on this tag type, I fetch the information. What is the device storage? What do I need to store this device? The second one is, what do I need to configure it? And with this information, I go in a template class which defines more or less my API. It gives me some functionalities like init and write, or read in some cases. And this is now the same for each tag type, which has the possibility over some traits to give me the information. One interesting note is line 8. There is a getter for the device type. This is quite important if you're making a hardware abstraction layer. You will not get all functionality in hardware abstraction layer in the first try, which means if some developer which develops something for you cannot access it over your hardware abstraction layer, he will not use your hardware abstraction layer. And then everything was for nothing, which means you cannot restrict on hardware abstraction layer, but you can at least make it coordinated. If you provide a tag type, you can every time make a type trait which gives you some information about your system on a chip, and you can every time return the base device type, which is then hardware dependent, but at least you can develop further and you can fix your HAL later on. So now, what have I achieved with this approach? I now can easily make template specialization. With template specialization, I can say my tag type is, for example, I'm now a G-test. Then I can change the whole behavior of my template code. And with this behavior change, I can define different configuration data. This means I can inject data from the outside into my object, can store them as pointer reference or whatever I like. And also I can use inheritance to extend the functionality, and I can completely change the behavior of my object. So, and then the interesting thing is templates are not easy to use. We had some problems with the acceptance of templates in the company. But you can make them look like normal objects. This is what I would do for the abstraction layer on the higher level, which means you have one level where you know what is your SOC, where you know what you want to achieve for your system. And this is more or less when your board configuration is complete, you know everything. And then what you can do is simply include what you want, make an alias that it's from your base GPIO with template type, you have a simple GPIO, and everybody which uses it based on this GPIO can simply use it. He does not need to care that this is a template or something. He can simply use it. And to create such files, you can use other tools. One example is, which is quite successfully used by Sapphire, is the device tree. Device tree has most information you need to know about your board in a more or less defined manner, which means you can pass the device tree, create your template code and your alias code to it, and can use this for your product. So, what do you need to remember about writing in hardware abstraction layer? It's a lot of effort. It's not so much fun like you think from the beginning. It's a lot of effort. You need to choose flexible abstractions. It is very hard to do right. Then you should hide your complexity from the user, because user want a simple life. They don't want to care about your template parameters. They don't want to care about some ugly include tricks you have done. They only want a simple API to use. And consider tests and simulations right from the beginning. If you miss this, you will lock out testing for your hardware completely. And you should think about code generation. It's quite a lot of code you need to write, which is often some kind of boilerplate or glue code. And you should consider code generation if you found a possibility to do it. So, now to the next layer, the middleware abstraction. Middleware abstraction has some quite interesting tasks. With the middleware abstraction, you have the possibility to lead the design of your business logic. What do I mean by that? Leading the design means what you provide in your middleware abstraction is what most quite possibly will be used on higher level. Which means, for example, if you favor a fiber over a thread, the possibility that you have fiber in your business logic will increase dramatically. Which means, here, differently to the hardware abstraction layer, you should only provide the functionality you want. And you should provide that in a way that you can easily configure everything which is relevant for the overall system. Which means, if you want heap allocations, it should not be done inside of the business logic. It should be provided from the outside via an allocator or something. If you have something to configure for priorities or stacks or such things, you should be sure that this will be done outside. So how could this look like? These are two APIs for thread creation, one for Sapphire, one for FreeAtlas. Like you see from the definitions, they look a little bit different, but more or less they are quite similar. Which means both need information about the stack, both have some information about the priority. They provide the entry function plus the user data. This is nothing I would provide from my middleware abstraction. What I would provide would look like something like the first code example. You have a thread configuration which is based on the stack information and is based on the priority. And this needs to be injected. Why should I inject it? The reason is quite simple. If you have it separate, you can you can make restrictions about the construction. You can enforce that it's only constructed by some special objects or such things. And this allows you to take over the control over this kind of configuration completely. In the second code example, you simply use how you want to simply see how you would use it, which means in the constructor you need to provide the configuration. And one time on the system level, you need to instantiate the configuration. So, regarding the middleware abstraction is an abstraction over all third-party libraries and over your operating system. So, now some notes about the standard template library. Standard template library itself is no third-party library. It's more or less the library from your language, so you should use it. But it could make sense to include it in your middleware abstraction. The first thing is quite simple, backporting. If you have different products with different lifetimes, there are the possibility that you want to use some features which are not available for each product. Span is one example, which means it could make sense that you backport it into your middleware abstraction, that it is available for every user. The other point is some people don't know what they can use from the standard template library, which means the freestanding proposal is not so good in the current state, which means some people have problems to know what they can use. If you have such people in your team, it could make sense to use some kind of aliasing in an own namespace that everybody does not need to think about it. You can simply use what you provide. This is effort. This is not has no high complexity, but is effort you need to do, and you can consider under one promise. This only works if your code style from your middleware abstraction is the same like the code style from the STL. Else you need to match all the code into your own code style, and this will be quite a task. So consider it if you think it's useful, but remember you should not mess up your code style. So summary. The most important thing, lead the design decisions for the business logic. Then consider this is something I missed. Consider the host system, which means, for example, if you make a middleware abstraction and you have an RTOS in it, the host system should still build. You should be able to build a binary on the host system. This is especially important for something like unit testing. You should take care about everything behavior relevant, which means resources, priorities, and such things. And you should only provide what is really necessary. So the next layer is the business logic. The business logic I distinguish between three parts. The first part are more or less components. Components is your normal logic element. This works more or less event-driven. You get data in, data is processed, you get data out. You don't care about your real hardware here. This is real algorithmic part. This interacts more or less with high-level drivers. High-level drivers are drivers which you push up to the component level, which means they have already done their thread transitions. They don't act in interrupt, but they can interact on the same level of the components and more or less share the same abstraction in the API. And then there's the system setup. System setup is what is more or less responsible for the resource handling in the end, and for the initialization and the startup of all your components and all your hardware drivers. So if you want, one thing, you see the arrows are communication paths. You see we have bidirectional communication, and nearly everything in the system needs to communicate with something, else it's dead. So if you want to achieve this with the primitive inheritance variants, so with interfaces, you will completely mess up your high-level drivers. Like you see is, you have some sensor which wants to log some data and which would send out his height. If you use it in a normal object-oriented way and would directly connect it with a UART, your UART has now a dependency to your sensor which will not allow that the sensor can print out something over I2C or such things, which means this is not a good approach, and this approach could also end quite badly. If you want to log something and you log it over an UART and your log message would block, the log now affects your overall behavior. For the integration part, if you only see interfaces, you don't know it. You can hope that the person which provides you the interface has thought about it and has fixed it on this side, but you cannot know it. There is a simple solution for that. The simple solution is, again, a different level of abstraction. Each communication over an UART or such thing has some kind of protocol, which means your data will be provided in some defined way, and we can hijack this for our information. The protocol needs to know how to encode and send a message, and the protocol needs to know how you can decode and dispatch a message. Which means, with a protocol, we get something which looks quite similar to this. If you never have seen this, this is the so-called room pattern, a quite old pattern. In a book for 20 years, it was already called an old pattern, but it's quite interesting. What it does, it was one of the approaches for an object-oriented model to abstract the sending interfaces, which means, in general, the main focus is the blue block. The blue block provides the communication layer. This could be a socket, this could be a UART or whatever, which is connected to a sender and receiver, which is not directly known by the sending component and the receiving component. This model can be simplified. Then it will look simple like that. Maybe somebody has already seen this. This is more or less how microservices also interact. What happens is a sender object has an outcoming message. The outcoming message goes in the message port, will be transferred to an incoming message to the receiving object. And the same the other way around. So this is something we can implement. And it could, for example, look like that. The only thing we care about is the writing functionality. The writing functionality needs a protocol, and it needs to know how to dispatch the messages. This is not so advanced like the dispatching talk from the morning, but bear with me. What we have is in line 4, we fetch over a trade all message types from the receiving object which is able to receive. So what now happens is we provide a write functionality, which can more or less only be called with all messages which the receiving object can receive. And in the line 12, we convert this message to the output protocol. And the output protocol will then simply call a free function which is able to receive the object based on both object types. The good thing about this approach is you don't need to call the function directly. If you call the function directly, you end up with overhead, but not so much overhead. But you can go forward and can add message queues or interprocess communication to really configure your system like it should behave. So from the receiving part, the only thing we need to provide is trades with some kind of type sequence over the incoming messages, and free function which dispatch the messages more or less automatically. The compiler can do the dispatching for us here. So the sending part is a little bit interesting. For the sending, we have our protocol. Our protocol is more or less now the write port. The write port can use inheritance to provide the interfaces. This is one possibility, which means here what you see is we have an abstract interface. The write port inherits from the interface, and then we can inject it in our component. The component is simply some kind of element in the business logic which wants to write something. We can also do it with type erasure. This would look similar like this. This is more or less the type erasure from Klaus Igelberger. He has explained it, I think, out in the CPPCon last year. This uses manual virtual dispatching, which means the line 4 more or less creates us a tuple of messages which we want to send. And for each of this message type, we create a lambda function. A lambda function will store a function pointer inside of a tuple. And what then happens is, if the write function is called, it fetches the write function pointer based in our tuple and simply calls our write port. Which means the component does not need to know anything, and the write port does not need to know anything about the component, which makes it quite flexible. And this is how the whole thing would look like. The write port is created in line 17 based on, in this case, UART driver and some kind of in-house protocol, and is then simply provided to the component in line 5. If you set this up this way, you can now on the system level combine all your resources, all your components with each other over different kind of write ports, and you can vary it however you want. Which means the only thing you need to know is that something can receive some kind of message and something can send some kind of message. You don't need to know what kind of messages, you only need to know, can I convert it or not? And this is everything you need to know about this. To sum it up, in the end, if you want to write reusable firmware, you should consider all possibilities for changes, which means all levels: business logic, middleware, and also all your hardware level. You should isolate the hardware and take control over the hardware abstraction. You should isolate the middleware and try to lead your business decisions, so business design decisions, and you should consider to design all your components as independent as possible, that you can interchange it later on. And don't forget to consider testing all over the place. With this, what's next? I'll first provide you a link where I will provide the slides, I think, tomorrow somehow. So until tomorrow, I will provide the slides to this link, and also will add some code examples after I clean them up, which means if you want to see how the port really works and not so quickly like now, you can look at it. And in distant future, I plan to play around with a hardware abstraction layer and also a device tree parser for this manner, and try to create a generic system setup. When I have this in somewhat showable state, I will also provide it on my GitHub, and probably in this first repository I will provide links, but this is distant future, this will take some time. So the next part, if you want to know more about this topic, I highly recommend these books. The first two books are from Jakob Beningo, which are quite interesting. He has a little fetish to see, so if you are not bothered by that, they're a good read. Klaus Igelberger's book explains type erasers very well. And the last two books are a little bit older. Real-time design pattern is where you find the room pattern. There are only two books I know which mention this pattern at all. And real-time C++ is also a great book, which gives some interesting ideas what you really can do with C++ on lower levels. And with that, if you want to learn more about Leica Geosystems, you can use this QR code, or you can ask somebody of Leica, which has this recruitment card. And with this, thank you very much for your attention. Any questions?
Thank you very much for your talk. Any questions? One. Two.
One question, that you have this big middleware layer where you somehow mix up different things. Does it make sense to make smaller abstractions there? Because in the end you ended up with some what you called high-level drivers, which are in the end only components. Yeah, if you would say I have an abstraction for the operating system, or I have something for communication mechanisms.
Yeah, maybe it was not completely clear. Those are different things. The middleware abstraction is only the abstraction about your third-party code and the abstraction for your operating system, such things. Everything regarding components and high-level drivers is your business logic. This is what you do. What you have for abstractions inside of your code on the business logic level is completely up to you. It should be for sure be independent to each other. But this is not the middleware. The middleware is everything you are not responsible for, but you need to border with the changes.
Thank you very much. Further questions?
You spoke about the hardware abstraction layer and how it's really hard to design one that works for all your targets and for all your features. So have you written down what you ended up with and what decisions you made?
The point is, yes, the hardware abstraction layer is quite difficult. What I currently try is, I want to use an Atmega 8 and an STM32. And if I create a hardware abstraction layer which can support both, at least for some things I'm considered for changes. But in general, what you need to do for the hardware abstraction layer is you need to try something and extend it over the time, and you will see where you fail. This is a process. This is nothing you will do overnight.
Further questions? Then thank you very much for your talk.